Hello everybody. We're going to continue our lessons on integration by talking about section 19b, which is about the area between two curves. And to do that, to calculate the area between two curves, we need a little bit of background in what a Riemann sum is. Okay, so a Riemann sum has to do with how we calculate the areas under a curve. You might remember from the beginning of the year, we talked about, we saw a video where the girl talked about finding the area under curves using these rectangles. And we made that comparison earlier in this unit as well. So one of the ways that we can find area under the curve is to think about filling that area with a bunch of small rectangles. Okay, and we talked about having the upper rectangles and the lower rectangles and finding an area between them. In this method, they're using the midpoint of the rectangle to find kind of the middle height of the rectangle. And so essentially, if I want to know the area under the curve, I can take the sum from k equals 1 to n, okay? So each of these rectangles is a k, so this is k1, k2, xk1, xk2, xk3, etc. So adding up all the rectangles up to n, and the rectangles all have an area of a base, which is the change in xk, okay? That's like the difference between this end and this end, that's why it's a delta. So they have a base times a height of f at xk. Okay, the height of this rectangle is however much the function equals when x is whatever this value is. So really this is just add up all the rectangles, base times height, okay? And we know from our work so far that we can do that by finding the integral from a to b of f of x dx. The dx represents the amount of the base of the rectangle. F of x represents how high each rectangle is, and the integral does this work of summing up. Okay, now what if I want to find the area between two curves? So suppose f and g are continuous functions on an interval ab, and f of x is greater than g of x for all x's between a and b. So in this case, the blue function f of x is higher than the brown function g of x for all of the values that we care about between a and b. This means that the two f of x lies above the curve g of x, and the two never can touch but never cross, and I want to find this area. So we could use a similar strategy. We could make rectangles that go between these two curves. Okay, they can still have this width of change in x or delta xk, but the height would be f of x, okay, whatever this value of f of x is, that would only be from the x-axis up to here, subtracting g of x. G of x would be the distance from the x-axis down to this bottom curve. Now, in this case, if I was subtracting those two values, I'd really be adding them together, right? I'd be adding together f of x and then have a negative g of x value. So when I'm subtracting a negative g of x, I'd get a positive. But if I took the difference between those two values, I'd find the height of the rectangle. And I could use that same system. Okay, so the area would be this. I'd have to do that for each rectangle here. I'd have to multiply the base times the height, and the height of the rectangle would be f at x minus g at x. Okay, remember that if I'm summing up all of those, it's the same as saying the integral. Okay, so that's what we said that's what I was getting at. Okay, if I try and make as many tiny rectangles as I can, so in other words, I'm taking that delta x and I'm making it approach 0, then I'm going to have a lot of rectangles that I'm summing up. Okay, that's the same as taking the integral from a to b of all of the bases, which is delta xk times the height, which is f at xk minus g at xk. In other words, if I tidy it up a little bit, that delta x becomes the dx, f at x minus g of x becomes our function, and I take the integral from a to b. Okay, so that's our area formula. Okay, and we'll take a look at the examples in the next video.